Hi everybody, the purpose of this video is to go over section 6 of chapter 4, and we are going to talk about applications and specifically models of exponential growth and decay. So yes, these models are going to use the exponential function. And these models will have this general format. It is our dependent variable y is going to be equal to some initial value, y naught, which is the amount of the amount of whatever is present at time 0, and that's going to be multiplied by the exponential function e raised to some constant k times t, where t can be in any unit, seconds, years, or whatever, depending upon the problem at hand. Now, if k is greater than 0, then clearly as t increases, y is going to become larger and larger, so we have growth. Conversely, if k is less than 0, then we have a problem of decay. And this is our first example. How long to the nearest day will it take for any quantity of a radioactive material to decay to 25% of its initial amount, knowing that it decays according to this particular function where t is the time in days? If that's the case, then 25% of its original amount basically means that a of t is going to be equal to a naught divided by 4. That's basically 25% of the original amount. Okay, so that basically sets up our equation. We are going to have that a naught over 4 is going to be equal to a naught times e to the negative 0.056 t. Of course, these will cancel. And what we're left is 1/4 is equal to e to the negative 0.056 t. Now, once again, we're trying to figure out what t is. And to make that happen, we have to get t out of the exponent. And we can do that by taking the natural log of both sides. So I'm going to take the natural log here, and I'm going to take the natural log here. What I will have over here is the natural log of 1/4. So really nothing exciting on this side. However, on the right-hand side, I can use the power property of the logarithm and write this as negative 0.056 t times the natural log of e. And what is the natural log of e? Well, that is nothing more than 1. Therefore, we will have that the natural log of 1/4 is equal to negative 0.056 t. I can now divide both sides by negative 0.056. These will cancel, and then I will have that t is equal to the natural log of 1/4 divided by negative 0.056. This will be a positive number because the argument of the natural log is less than 1, so this will be negative, and we'll have the division of two negative numbers, which will give us a positive number. And if we actually computed this, we would have that t is equal to 24.7, and that is going to round up to 25 days. Okay, for our next trick, we are going to look at an example that finds the time for the amount of an investment to double. So here's what we got. How long to the nearest year will it take for the money in an account that accrues interest at a rate of 2.25% compounded continuously to double? Of course, to do this problem, you need to know the formula associated with continuous compound interest, and that formula is that the value in the future is going to be equal to the amount that you put in, we're going to call that P, times e to the RT, where R is the interest rate as a decimal, and T is time in years. Okay, so what is R? Well, R is 2.25%. However, we need this as a decimal. To do that, we'll divide that by 100, and that will give us 0.022 What is A? Well, remember we want to find the amount, the time required for the original amount, which is P, to double. So A is going to be equal to 2 times P, and once again we are looking for T. Okay, so making the substitutions, we will have that A, which is now 2P, is equal to P times e to the 0.025t. The p's cancel, and then we have 2 is equal to e to the 0.025t. We now once again want to take the natural log of both sides. So we're going to take the natural log here. We are going to take the natural log here. And we will have that the natural log of 2 is equal to 0.025t times the natural log of e. Once again, the natural log of e is equal to 1. And then we will have that the natural log of 2 is equal to 0.0225 times t. I forgot the extra 2 there. And then dividing both sides by 0.0225, we will have that t is equal to the natural log of 2 divided by 0.0225. Now notice at the bottom is the interest rate as the decimal. The top is the natural log of 2, and that occurs when we want to find out how long it takes for the money to double. If we wanted to find out how much long it takes for the money to triple, what would that be? Well, that would be that t would then be equal to the natural log of not 2 but 3, but r would still the same, divided by 0.0225. But that's another problem. Actually, it's a problem in your homework, so you might want to keep that in mind. Now, computing this one, we are going to have that t is equal to 30.8 years, and since you want to round this to the nearest year, that will be 31 years. The next collection of problems we're going to be dealing with are decay function models, and these tend to be used to model the decay of radioactive material, but they're also can also be used to model the depreciation of an asset like a house, a computer, or a car, or any other tangible asset. And this actually comes in handy when you do your taxes. For example, if you purchased a computer for work, and well, if you do, that computer is going to depreciate over time, and that depreciation, according to the IRS, is a loss, and you can write that loss off on your taxes. So it has a few practical values has a certain practical value when you become older and have to do have a more complicated tax situation. Now, typically, particularly in the case of radioactive material, this is based on the half-life of a substance, and that half-life is used to determine K, which is what we're going to do in our next example. Here it is. Suppose we have 800 grams of a radioactive substance that is initially present, and that 2.5 years later only 400 grams remain. Well, then that is our half-life. We would say that our half-life is 2.5 years. The first thing we want to do is to determine an exponential function that models this decay. Well, that function is going to have the form y is equal to y naught e to the k times t. Okay? Now, we know that y naught is 800 because that's the initial amount. So this is going to be y is equal to 800 times e to the k t. We also know that at 2.5 years, the amount y is going to be 400 grams. So we can use that in our equation. That's going to give us that 400 is equal to 800 times e to the k times 2.5. K is k, t is 2.5. And that is going to reduce to 1/2 is equal to e to the k 2.5. All right, now once again we want to take the natural log of both sides to get the get the k out of the exponent. So we're going to have the natural log here. We're going to have the natural log here. And that is going to give us that the natural log of 1/2 is equal to 2.5k times the natural log of e, which of course is equal to 1. And that will give us that k is equal to 2.5 divided by the natural log of 1/2. And when you computed that, and if you compute that, you will get that k is equal to negative 0.27726. And I wrote it to 5 decimal places just to play it safe. And that means that our model is going to look like this. It's going to be y is equal to y naught, which is 800, times e to the negative 0.27726 times t. Okay, so that is our model, and we can use this model for part B. Part B says how much of the substance is present after 4 years? Well, that tells me that t is equal to 4. And then all we need to do is substitute 4 for t and see what y is. And then we will have y is equal to 800 times e to the negative 0.27726 times 4. And that will give us that y is equal to 263.9 grams, 3.9 grams, which will round to 264 grams. Okay, now in our last class we talked about Newton's law of cooling, and we're going to use it in a little more detail here. And this is how it works. Suppose that you have a body like a coffee cup or something that is placed in an environment with a certain temperature. Then the amount that that body cools, or that quantity cools, is basically governed by this particular equation. So if you actually took a cup of coffee and put it into a freezer, then how quickly the cup of coffee cools is actually governed by this equation, where T is the temperature of the environment that it is placed in, and then C and K are constants, and of course T is time. And with that, we are going to mess with this particular example. But to do this, I'm going to have to do this in OneNote because I don't think I have enough room here. Okay, so here we are back in OneNote, and this is what we have. We have that a pot of coffee with a temperature of 125 degrees is placed in a freezer with a temperature of 0 degrees Celsius, which is actually not very cold for a freezer since that's basically the freezing temperature. After 15 minutes, the temperature of the coffee is reduced to 37 degrees Celsius. And we want to use this information to write an equation for the model. And we can do that. Now, notice that, recall that T0 is the temperature of the environment that it is placed in. Therefore, and we're placing a cup of coffee into a freezer with the temperature of 0 degrees Celsius. So T naught is equal to 0. And that basically tells us that f of t is equal to some number c times e to the negative kt, where once again t is in time. All right? Okay, so now what we have here is that at the time 0, the cup of coffee is 125 degrees Celsius. So we know that f of 0 is equal to 125 degrees. Well, that is also equal to c times e to the negative k times t, which is 0. And that implies that c is equal to 125 degrees. Okay, so that tells us that f of t is equal to 125 times e to the negative kt. Okay, now this is where this part comes in handy. After 15 minutes, which by the way is 1 hour, so t is equal to 15 minutes, which is equal to, well, 1 over 60. This will be equal to 1/4 of an hour. All right, so we have that f of 1/4 of an hour is equal to 37 degrees Celsius, which is equal to 125 e to the negative kt. Now I can divide both sides by 125, and I will have that 37 over 125 is equal to e to the negative, and actually t over here is 1/4, so I can actually write this as 1/4 e to the negative k over 4. And then we can just clean this up over here. This should be e to the negative k times t, which is 1/4. Okay, once again, we're going to take the natural log of both sides. So the natural log here, the natural log here. This will give us that minus k over 4 is equal to the natural log of 37 over 25, or that k is equal to negative 4 times the natural log of 37 over 25, which, by the way, is equal to 4.870. Okay, so that's part A. Now, part B is to find the temperature after 20 minutes. Well, first, I have not finished part A yet. I need to finish writing the model, but now we can do that because now I know what k is, and that is going to give us that f of t is going to be equal to 125 e to the negative 4.870 times t. Okay, and with that in mind, we can figure out, we can do part B. In part B, we want to figure out the temperature 20 minutes later. Okay, well, there would be, if that's the case, then t is going to be equal to 20 minutes, which is equal to 20 minutes times 1 over 60 minutes in 1 hour, which is going to give us 1/3 of an hour. Okay, so with that in mind, we will have that f of 1/3 is going to be equal to 125 raised to the e, or raised to the times e raised to the negative 4.870 times 1/3. Okay, so all we need to do is knock this out in our calculator, and if we do, we will get the value of 24.66 degrees Celsius, which I think we could round to 25 degrees Celsius. And then for the last part, we want to figure out how long it's going to take for this to cool to 11 degrees Celsius. Well, once again, in this case, f of t is going to be equal to 11. And that's going to be equal to 125 e to the negative 4.870 t. And once again, we need to solve for t. First thing we're going to do is divide both sides by 11 by 125. That will give us 11 over 125 is equal to e to the negative 4.870 times t. I can then take the natural log of both sides. And then according to the property, or the power property, this is going to be equal to negative 4.870 times t times the natural log of e, which by the way is equal to 1. And over here we're going to have the natural log of 11 over 125. Okay, so now we want to divide both sides by negative 4.870. 4.870, negative 4.870, and then that is going to give us that t is equal to the natural log of 11 over 125 divided by negative 4.870, and that is going to give us 0.499 hours, which will round to a half of an hour. And that brings me to my final trick. Before I do that, let me bring this back to our... Okay, and here is our final trick. Suppose that in a certain area, the consumption of electricity has an increase at a continuous rate of 6%. If it is to continue to increase, typo there, at this rate, find the number of years that will pass before 4 times as much electricity will be needed. Okay, well, the first thing we need to do is figure out what the actual growth formula is for this. And that is going to be that y is equal to your initial consumption. We're going to call that CO times e to the RT. So it's just like the continuous compounding problem. Now here R is 6%, but we can't use that. We can't use R as a decimal, so we need to write as an equation. So we need to write this as a decimal. That's going to be 0.06, and y is going to be equal to 4 times 0, because 4 times C naught, because we want to know how long it's going to take for the electricity consumption to increase by a factor of 4. So y is equal to 4 C naught. And what does that give us? Well, that gives us that y, which is now 4 C naught, is equal to C naught times e to the 0.06 times t. Obviously, the C naughts cancel. I can take the natural log of both sides. That's going to give me the natural log of 4 is equal to the natural log of e to the 0.06 t. Using the power property, I will have the natural log of 4 is equal to 0.06 t times the natural log of e, which, by the way, is simply 1. And then we will have that t is equal to the natural log of 4 divided by 0.06. And that will give us 23 years. And that covers all of the material that we wanted to discuss, that I wanted to discuss relative to this particular section. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.